Seventh graders, take out your 2.5 square root notes and join me. I have a question for you today. How do I read that? We talked at the beginning of the year how important recognizing math symbols is, and also math is a language. And we understand it more and more by practicing it, being exposed to new pieces within it, and learning about them. So with that said, this is a radical symbol. With a lot of things in life, there are also other names for this symbol. For example, it can be called a square root symbol, a cube root, a fourth root, a fifth root. When you just have the plain symbol, it's implying that you're looking for the square root. If it's any other root, it will be denoted by a small number in the V part of the radical symbol. So my guess is that you've seen a movie or a show where people are writing fancy math problems all over the board and this symbol has come up and it makes the problem look really challenging and difficult. Well, I am here to tell you, since you already know a lot about taking a value and squaring it, taking a value and raising it to the second power, you already know a lot about square roots. Square rooting a number is the inverse operation of squaring a number. What do you mean by inverse operation, Mrs. Kluber? Well, take a moment. What will undo any addition problem? Subtraction. And what will undo any subtraction problem? Addition. How about multiplication? What will undo that? What's the inverse operation of multiplying? Dividing. And vice versa. Well, the inverse operation of taking a number and squaring it is finding its square root. And vice versa. Let's take a look at a problem. Nothing you need to write down yet in your notes. Let's take 3 and let's raise it to the second power. We can also say 3 squared. And well, what's the value of 3 squared? Well, that's 3 times 3, which is 9. Now, what if you wanted to go the other way with this? You wanted to ask people, hey, what times what gives me 9? Is there a way that we could show that in math? Is there a symbol that we could use to undo squaring a number? You bet. It's the square root symbol. So we can go, we want to know what times what. That what times what has to be the same number. What times what gives us 9? Well, then we want to take the square root of 9. What's the square root of 9? Well, think when you took 3 and you squared it, your base was being multiplied 2 times in your multiplication problem, right? So when you are square rooting a value, you're looking for the base. The square root of 9 is 3. And I can do this square root thing again. Let's say I want to know 4 squared is 16. So if I want to do the inverse of squaring the 4, I got 16 when I squared 4. If I want to go, well, what times what gives me 16? A way I can write that is using the square root symbol. I want to find the square root of 16, right? So I'm thinking, what times what gives me 16? And that what times what has to be the same number. Well, that's 4. And we could keep going. We could go 5 and square it. So my base now is 5. And I'm squaring it, and we know 5 squared is 25, so if I want to go, hey, what times what gives me 25, I'm thinking then, what's the square root of 25? And, well, that would be 5. It's undoing the squaring. Let's think about this the opposite way right from the get-go. So what if I gave you this problem? You see that square root symbol, so you're thinking, what times what gives me 36? What when I take to the second power gives me 36? Well, we know 6 times 6 is 36. So the square root of 36 is 6. What about when those negative or minus signs are involved, Mrs. Kluber? I haven't seen an example of that yet. Well, I want to remind you to not forget what you already know. And we have worked with problems like this, right? Where we're taking the opposite of 6 squared. So we get 36, and now we want the opposite of that. I could have square roots that do this, where I'm looking for the opposite of the square root of 36. Well, what's the square root of 36? 6. And now what's the opposite of that? Negative 6. So don't lose what you already know. This square root symbol, this radical symbol, is the principal symbol when you see just this. But sometimes you'll see this on the outside of the square root symbol, and that's referring to the positive or the negative. Let's talk about that for a moment. If you don't see anything, it's called the principal symbol. It just is looking for the positive. But you might go, well, you know, Mrs. Kluber, it could be negative 6 that you're squaring, right? Because that's going to give you a positive 6. And 6 squared, that gives you a positive 36. How do you know which one it is? Well, that's when you want to pay attention to any of the signs that are going on outside of the radical symbol. If it looks like this, it's wanting just the positive. If it looks like this, it's looking for the opposite of whatever you are taking the square root of. And if it's looking for this, it's looking for both the principal and the opposite. Oh boy, see, math symbols, signs are so important to learn and work with, aren't they?
So our goal today is to be able to recognize and calculate perfect squares and non-perfect squares. We just talked about what square roots are. So now let's dive into our notes. Look at that first chunk. Those examples that you see are all perfect square roots. What do you think makes a perfect square root? Based off of my intro that I just gave you. A perfect square is made by squaring a whole number. It's the inverse operation of squaring a whole number. See if you can find the square root symbol. So if you are using the TI-30XS Multiview, you're going to first have to hit the second button, and then the square root symbol is the same as the squared symbol. But do you see how the square root symbol is in green just above the button? When you hit the second button, that activates the square root symbol. One more thing, on your TI-30XS Multiview calculator, go to mode and make sure that the mode, when you go down, is on classic instead of math print. That will be helpful when we're working with square roots. So again, make sure it is on classic. Go to your notes and find the perfect square roots chunk. Perfect square roots are where you take a whole number. We like working with whole numbers, don't we? And you square it. So your answers are going to be a whole number. You'll see that the first four are done for you. I did the square root of 25 earlier in the video, and I did the square root of 36 earlier in the video. But I want to model doing those two using your calculator. So first of all, identify where your square root key is. If you're using the TI-30XS Multiview like I am, remember we have to hit second first and then find our square root key, which it's on the squared button, hence it's the inverse operation of it. So I want to find the square root of 25. It's 5. Do you see how you entered in on your calculator? I'll do one more with you. The square root of 36, we already know that that's 6, but let's type it in our calculator. Maybe you have to hit the second button first to activate your square root key. 36, 6. What I'd like you to do is pause the video and use your calculator, or maybe you don't need to use your calculator, to find the remaining perfect squares that are in your notes. Go ahead and check your perfect square root answers with mine and make sure you have them filled in your notes accurately. Now, we could go on and on forever, right? Numbers go on and on for forever, so perfect square roots are going to go on for forever. But if we have something called perfect square roots, then I bet you're already guessing there's something that is a not so perfect square root. So go to the second chunk in your notes. Let's investigate non-perfect square roots. So a perfect square is when you take a whole number times the exact same whole number and you get a whole number, right? Well, here we have non-perfect squares. There is no number times itself that gives you 45, right? So it's not a perfect square. However, we can use perfect squares to help us estimate, to get an approximation for non-perfect squares. So that's what I want to start with. We have the square root of 45. We know there is no number times the exact same number that gives us 45. So I want you to go to chunk 1 in your notes, find between what two perfect square roots could you sandwich the square root of 45? The square root of 36 and the square root of 49. You could sandwich the square root of 45 in between those, right? Yeah, so now what two integers are the square root of 36 and the square root of 37? Well, that would be 6 and 7. That means, 7th graders, that the square root of 45 is somewhere between 6 and 7. And now if you look, 45 is closer to 49 than it is 36. So my guess is if I were to think about a number line, it's going to be like 6.6 or 6.7. It's going to be closer to the integer 7 than it is to the integer 6. So if we pull out our calculator, we can go the square root of 45, 6.708203933. So I'm going to take this value and I'm going to round it to the nearest hundredths place. And that's going to be my approximation for the square root of 45. So in the hundredths room, I have a 0. I need to look next door. Is this digit 5 or higher? Then I'm going to add 1 more to 0, which would be 1. So 6.71 is about the value of the square root of 45. Now, which one of these integers is 6.71 closest to? 7. You're right. So we could say the square root of 45 is about 7. Or in this case, we'll say it's about 6.71. Let's do the next example. We have the opposite, the square root of 30. There's no number times itself that gives you 30. So we need to think between what two perfect squares can we squish the square root of 30? I'm going to ignore the opposite sign for right now. Look at chunk 1. What two perfect squares can we sandwich the square root of 30 in between? The square root of 25 and the square root of 36. But now we're going to take the opposite of those, right? Because of this minus sign here. So what's the square root of 25? 5. So the opposite of that would be minus 5. What's the square root of 36? 6. The opposite of that would be minus 6. Now, that means the square root of 30, or the opposite, the square root of 30, is going to be somewhere between minus 5 and minus 6. Let's pull out our calculator. Let's go and let's find the square root of 30. And remember, we're going to take the opposite of that. So 5.477225557, da 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 da. So we're going to round to the nearest hundredths place. There's a 7 in the hundredths room. I look next door. Is this 5 or higher? Then I'm going to add one more, which would be 8. So 5.48. That is my approximation for the opposite, the square root of 30. Now, I need to make sure that I take the opposite of 5.48, which is going to be negative 5.48. Now, which integer, oops, it came in at the same time. Which integer, negative 5, negative 6, is this closest to? You'd be rounding to the ones place now. It's going to be closest to negative 5. Let's go to the last one. We have the square root of 3.45, the square root of 3 and 43 hundredths. So between what two perfect squares would you find this square root? Well, that would be between the square root of 1 and the square root of 4, right? Now we know the square root of 1. And what's the square root of 4? 2. So we know the square root of this non-perfect square, 3.3 and 43 hundredths, is going to be somewhere between the square root of 1 and the square root of 4. Now 3 and 43 hundredths, if I think about that on a number line, is much closer to the whole number 4 than it is 1. So my guess is this is going to be the square root of 3 and 43 hundredths is going to be much closer to 2 than it is going to be to 1. Let's see if my guess is correct here. So let's take the square root of this non-perfect square, 3.43. It is much closer to 2 than it is 1. So we're going to round to the nearest hundredths place. So there's a 5 in the hundredths room. If I look next door, is this digit 5 or above? Then I'm not going to give this 5 a shove because it's not, it's 2. I'm just going to keep it as it is. So this rounded would be 1 and 85 hundredths. So 1 and 85 hundredths. And which integer over here is that closest to? Yeah, you may have already saw that it came in 2. So the square root of 3 and 43 hundredths, we could say, is about 2, but a closer approximation would be 1 and 85 hundredths. So there is how you work with non-perfect square roots. You use perfect square roots to help you estimate the non-perfect square roots. Let's look at an application piece now. All right, so we have learned a new math symbol to add to our math repertoire, and that is the square root symbol, the radical symbol. We've learned what perfect square roots are. We've learned what non-perfect square roots are. Now let's apply. You want to create a square garden and fill it with flower seeds. The seed package says it will cover 115 square feet. What's the largest square garden you can create? Round your results to the nearest tenth. So we're trying to figure out what's the largest square garden we can create. So that means we need to figure out our dimensions. What does each side of our square garden measure in length? So I'm going to put my sentence as the dimensions for my square garden need to be blank feet by blank feet. So if I go line by line, are there any key operation words or words that just help me, that are going to help me move forward in this problem? You want to create a square garden. A square is a really nice shape, and it has some important properties, like all sides measuring the same length, and fill it with flower seeds. Nothing else there. The seed package says it will cover 115 square feet. That label is drawing my attention. I know that if I know the area of a square, I then can use that to help me figure out the sides of the square. Any important numbers in this problem? 115 because that's the area. Now my job is to figure out what each side of my square garden measures. So I'm going to let my width and my length, or my height and my base, just be x. They represent the exact same value, so that's why I use the exact same variable. When I take x and multiply it by x, I'm getting 115 square feet. So if I take the square root of 115, that will give me the length of just one side of my square. So let's go ahead and let's calculate the square root of 115. It is not a perfect square. So it's going to be somewhere between the square root of 100 and the square root of 121. The square root of 100 is 10. The square root of 121 is 11. So it's going to be somewhere. If I were to zoom in on a number line and see 10 and 11, it's going to be somewhere between there. Probably closer to 11 than 10. So let's go ahead and let's go the square root of 115. Remember, we're going to round to the nearest tenth. So 10.72380529, and it's going to go on. We need to round to the nearest tenth. My 7 is in the tens place. So if I look next door, it's not 5 or above. So I'm just going to keep it how it is. 10 and 7 tenths. Going back to my problem, the dimensions for my garden need to be 10 and 7 tenths feet by 10 and 7 tenths feet. Now, if we go and we do that, if we take 10.7 and square it, if I take 10 and 7 tenths and square it, that gets me pretty close to 115, doesn't it? It would be a little bit more. However, the directions do tell us to round to the nearest tenth.